So I have two very similar examples set up for this video. I'm going to first evaluate the integral of x times the square root of x plus 3 dx, and then the integral of x squared times the square root of 2x minus 1 dx. And the approach is going to be very similar in each of these examples, but I wanted to give you two examples to make sure you understand the overall process here. So focusing on this first integral, whenever you have one function of x inside of another function of x, then this is where you should consider integrating using substitution. So in this case, if we let u equal the inner function, x plus 3, then the differential du in this case would just equal 1 times dx. So in this case, this isn't often the case, but in this particular problem, du is just equal to dx. Usually there's some multiple of dx here. There's some kind of adjustment when we change the variables. Here, that's not actually the case. So when we want to write this as an integral in terms of u, this part here just becomes the square root of u. Dx right here is just directly equal to du in this case, but we still have this x out front. So in previous examples that I've shown, the x outside of the square root has become part of the differential. Our du is something like 8x dx, and so we need that x as part of the differential for du. In this case, we don't need that x, so the x is just kind of hanging around, sort of uninvited to the party here. It's kind of a sad way to look at it, but before we integrate, we need this written completely in terms of u. And so we cannot integrate this right now. We need to somehow, I have arrows going everywhere here, and I'd like to use another color. I suppose I'll use red. So the x right here needs to be written in terms of u. Well, so in order to do that, we should go back to our substitution equation, u equals x plus 3. If u equals x plus 3, then it's fair to say that u minus 3 equals x. And so we can change this x, trade that in for a u minus 3. And there you have it. I mean, now this is, here's your x times, we've got square root of u times du. So everything's in terms of u at this point. So that's the main takeaway in this entire video, is just that if you have this x where it turns out the du doesn't gobble up that x in this case, where the way it normally does, then what you can do is go back to your substitution equation, solve for x, plug in that expression of u in place of x. Now in order to find the antiderivative, there's no product rule for antiderivatives, and so we need to multiply this out. So this is equal to the integral of u to the first times this is u to the 1/2, right? And so when you add those exponents, you'll have u to the 1 plus 1/2, that'll be 3 over 2, minus 3 times square root of u, which is u to the 1/2. So all that happened on this step is I distributed square root of u, which is equal to u to the 1/2. Now I can apply the power rule for antiderivatives. So if I add 1 to the exponent here, too many markers in my hand like always, add 1 to the exponent here, so we're adding 2 over 2, that'll make this exponent 5 over 2. Put 1 over 5 over 2 in front, well that's the same as 2 over 5. Go ahead and put the reciprocal. Minus 3 times, so we go through the same song and dance here. Add 1 to the exponent, so that's 2 over 2. That gives us u to the 3 over 2. 1 over 3 over 2 in front. Well, 1 over fraction instead we'll just do times the reciprocal 2/3. My 5 got a little big here. I'm going to save some room. for the final answer. And now we tack on the plus c, the constant of integration, because now we've actually applied the power rule to find the antiderivative. And so the last remaining step is mostly just to take the u's in this answer and put back the expression of x that represents. Here I can also cancel these 3, so this is minus 2 u, but I'm about to replace that to the 3/2 plus c. I mean, there is a common factor we could factor out here, but that's not required. So this is x plus 3, u is equal to x plus 3. And this is fine to leave your final answer in that form there. So that's for this first one. Since that's kind of a new technique, I did want to show a second illustration of that technique over here. So in this integral of x squared times the square root of 2x minus 1. I'll need to just make a little room here. So in this one, again, we're going to let u equal the inner function. So let u equal 2x minus 1. Then the differential of u, du, will be the derivative of this, which is just 2, times dx. Alright, so when we try to translate this original integral in terms of x to an integral completely in terms of u, this will become, so this is just square root of u. Right, I'm going to go ahead and call it that. Now dx is equal, du is equal to 2 times dx. So dx by itself is equal to 1/2 times du. Right? If you divide both sides of this equation by 2, then dx is equal to 1/2 du. So the dx right here is equal to 1/2 du. And now, again, we've got this expression of x just kind of sitting out front, waiting for its name to be called. You know, I always think of this extra x left over as being a little pathetic. I don't know. It's just the way I give personality to these functions. But anyway, so the x squared is just kind of sitting over here hoping to get involved. Turns out we don't need it. So what you can do is go back to your original substitution equation, solve it for x. So this needs to be written in terms of x. So we say, well, if u is equal to 2x minus 1, then u plus 1 is equal to 2x. And so u plus 1 over 2 is equal to x. So this, let's see, x squared will equal, so this is x squared, u plus 1 all over 2 squared, times this is the square root of u, and then we've got our 1/2 du. So in this case it's still a bit of a mess, but it's at least completely in terms of u. So we've grown accustomed maybe to once we get it in terms of u, everything looks nice and easy breezy. Now our integrals in terms of u in these last two examples are kind of getting worse and worse. But that's okay, we can get through this one. Just going to take a little more effort than some of our previous examples. So the overall idea so far has been find the u substitution. We're sticking with the plan of letting u equal the inner function. If you have an expression of x left over, solve for x in your substitution equation and substitute that expression of u. Now we need to integrate that thing. So what I'm going to do next will be, well, I might as well toss this 1/2 out front. I'll keep it in blue to help show where it came from. Integral of, so if we've got this fraction squared, we can look at that as the numerator squared over the denominator squared. And so this is u plus 1 squared over 2 squared. Square root of u, which we can write as u to the 1/2 times du. All right, so this is 1/2 integral of, so u plus 1 squared. Keep in mind, so that's u plus 1 times u plus 1. So maybe you just know the form of a binomial squared, which is great. If you don't, then you can FOIL it out. So write it out long ways and then FOIL. That'll give you u squared plus 2u plus 1 over 2 squared in the denominator, so that's 4, times u to the 1/2 du. Constant denominator like this, I would bring out as 1/4. And then we've got u squared plus 2u plus 1 times u to the 1/2. Okay, here's where it's going to get maybe a little tedious, but I'm gonna work through it. If you kind of see where this is going from here, I wouldn't blame you if you'd stop the video at this point. But for you guys who like to see it through to the end, distribute u to the 1/2. When you do that, you add the exponents. So for example, u squared times u to the 1/2 will be u to the 2 plus 1/2, which I'll write the arithmetic here. So the exponent is going to be 2 plus 1/2. So that's 4 over 2 plus 1 over 2. So the exponent here is 5/2. We're not integrating yet, keep in mind. We're just distributing u to the 1/2. So u to the 1/2 times u squared is u to the 5/2. Plus 2 times u to the first times u to the 1/2. If you add those exponents, you get 3/2. And then plus u to the 1/2 times 1, u to the 1/2. Now we can apply power rule across this thing to get the antiderivative. So this is 1/8. Add 1 to this exponent, you get 7 over 2. 1 over 7 over 2 in front of it. Well, 1 over a fraction doesn't look real nice. Let's go ahead and change it to the reciprocal 2/7. Plus 2 times add 1 to this exponent, you get 5 over 2. So we would do 1 over 5 over 2 in front, or just times the reciprocal, 2 over 5. Add 1 to this exponent, you get 3 over 2, put the reciprocal in front. That's happened enough times, probably need to say less about it this time. So all of that plus c, now we've actually taken the antiderivative. You could factor out, and I think I will, factor out u to the 3/2. So these are all powers of u. So this is equal to 1/8 times, I'm going to factor out u to the 3 over 2, because it does make this look a little nicer. So if we take this antiderivative, factor out u to the 3/2. In fact, we could even factor out 2 times u to the 3/2. Why not? I'm going to take out a common factor of 2u to the 3/2. Then let's see what's left. So here I factored out the 2, so we're left with 1/7. Take away the 3/2 power, take away 3 over 2, and you're left with 4 over 2, which would be u squared. From here, we factored out 2, so you still have the 2/5. If we factored out u to the 3/2, then you're left with u to the 2/2, which is just u to the first. And then this last part, we factored out 2, so you're left with 1/3. U to the 3/2 was factored out. Plus c. All right, so final answer, 2 over 8, which is 1/4, times u to the 3/2. This is 2x minus 1. Times 1/7 u squared plus 2/5 u to the first plus 1/3. close up that brackets plus c. Yikes-a-rama, but there's your final answer, where the u's are 2x minus 1. There we go.